Today, we will learn about an important unit in catalytic cracking, the 4riser reactor. The 4riser reactor is where catalytic cracking reactions take place and is one of the key equipment in catalytic cracking units. There are two common forms of 4riser reactors: straight pipe type and folded tube type. The former is mostly used in high-low parallel 4riser catalytic cracking units, while the latter is mostly used in coaxial units or units converted from bed reactors to risers. The 4riser reactor mainly consists of the riser, disengager, stripping section, cyclones, and regenerators. The section below the feed inlet is called the pre-lift section. Its function is to introduce steam from the bottom of the riser, also known as lift steam, to accelerate the regenerated catalyst flowing from the regenerated catalyst inclined pipe, ensuring uniform contact when the catalyst meets the feedstock oil. This function is called pre-lifting. The 4riser reactor is a pipe 30 to 40 meters long, with the medium being oil vapor and catalyst, and an operating temperature of 500 to 550 degrees Celsius. The residence time of oil vapor is generally 2 to 4 seconds. Prevent erosion of the inner wall by high-velocity catalyst and reduce heat loss. The pipe is lined with 100 to 125 millimeters thick insulation and wear-resistant lining. The diameter of the 4riser reactor is determined by the feed rate. The gas velocities commonly used in industry are 4 to 7 meters per second at the inlet and 8 to 18 meters per second at the outlet. The height of the riser is determined by the reaction time. In industry, the reaction time is mostly 2 to 4 seconds. The upper outlet of the riser is equipped with a gas-solid rapid separation device used to quickly separate the catalyst from the oil and gas to suppress further reaction. So, students, think about it. Why is rapid separation of catalyst and oil vapor and gas? It is to suppress thermal cracking reactions. There are various forms of rapid separation devices, such as relatively simple umbrella caps or T-shaped components. Now, primary cyclones are more commonly used. In practice, the oil and gas vapor still has a certain residence time in the disengager and the transfer line. From the riser outlet to the fractionator is about 10 to 20 seconds, and the temperature is still high, generally between 450 to 510 degrees. Under these conditions, a considerable degree of secondary reactions still occur. The secondary reactions are mainly thermal cracking reactions, leading to increased dry gas yield and severe equipment coking. Severe coking can occur on the walls of the disengager, oil and gas transfer line, and the bottom of the fractionator. For heavy oil catalytic cracking, this phenomenon can be more severe. Therefore, shortening the residence time of oil vapor at high temperature is one of the effective measures to reduce secondary reactions, such as appropriately reducing the volume of the dilute phase space in the disengager and shortening the distance between the outlet of the primary cyclone's dip leg and the inlet of the cyclones at the top of the disengager, etc. To optimize the reaction depth, some units use reaction termination technology, which involves injecting a termination agent at a certain point in the middle part of the riser to lower the reaction temperature in the middle and upper part, thereby suppressing secondary reactions. Some also correspondingly increase or control the temperature of the mixing zone while injecting the reaction termination, known as mixing temperature control technology, or MTC for short. The key to reaction termination technology is how to determine the appropriate location, type, and quantity of the termination agent to be injected. Currently, most refineries rely on experience to determine the relevant operating parameter. The oil catalyst contact condition in the feed section at the lower part of the riser has an important impact on the reaction of heavy oil catalytic cracking. Reducing the atomized droplet size of the feedstock oil can increase the heat transfer area, thereby improving the vaporization rate of the feedstock. It can also improve the distribution of product yields. The function of the stripping section at the bottom of the disengager is to use steam to strip the oil vapor and gas absorbed on the catalyst, and to displace the oil and gas between catalyst particles. The function of the stripping section is the same as that in distillation columns, both to reduce the oil vapor partial pressure. The efficiency of the stripping section is related to the steam usage, the residence time of the catalyst in the stripping section, the temperature and pressure of the stripping section, and the surface structure of the catalyst. Currently, 4riser reactors still have inherent drawbacks. Excessive riser length worsens product distribution because it aggravates thermal cracking reactions. Catalyst coking causes the catalyst in the latter half of the riser to be in a state of low activity and poor selection. Fresh feedstock and recycled slurry oil compete for catalytic active centers. For conventional risers, it is difficult to achieve high catalyst T-to-oil ratio operation. On this basis, we proposed the concept of a two-stage riser to improve the effective activity and selectivity of the catalytic cracking catalyst, thereby improving the distribution of desired products. It can be carried out in stages, increasing the flexibility for adjusting production schemes. Therefore, the two-stage riser, TSR, FCC technology broke the original riser reactor form and react flow. The two-stage riser reactor replaces the single reactor, constituting a reaction regeneration system with two circulation loops. Let's look at the process characteristics of the two-stage riser. The first stage feeds fresh feedstock, while the other stage feeds recycled oil, both contacting and reacting with highly active regenerated catalyst. Both stages react when the light oil yield is maximized, ensuring maximum yield of the target products. When there is a need for gasoline olefin reduction, gasoline can be recycled and reformed in the second stage. Comparing the industrial test results of two-stage versus single-stage, we can see that the light oil yield increases by more than 4 percentage points. The diesel yield increases by more than 3.5 percentage points. Because the riser is shorter, reaction time is somewhat reduced. The liquid yield increases by more than 2.5 percentage points. The dry gas yield decreases significantly improving the diesel-to-gas ratio. Furthermore, flexible and diverse operating modes can be adopted. Besides the two-riser process, we will now learn about the MIP process. The MIP process adopts a new reaction system with a series riser reactor form and corresponding process conditions to selectively control cracking reactions and promote hydrogen transfer reactions and isomers. The main purpose of these two reactors is to reduce the olefin content in catalytic cracked gasoline. The process characteristic is dividing the reaction system into two reaction zones. The first reaction zone is mainly for cracking reactions, using higher reaction temperature and higher catalyst-to-oil ratio to crack heavy and produce more olefins. The second reaction zone mainly enhances hydrogen transfer reactions and isomerization reactions. Both of these reactions are exothermic and relatively slow. It uses lower reaction temperature and long reaction time. MIP technology can significantly reduce the olefin content in gasoline, while also increasing the isoparaffin content in gasoline. The liquid yield is relatively high. The content we learned in this section includes types of risers, structure and characteristics of the riser, two-stage riser technology, and MIP process technology. The above is the learning content of this lesson. Goodbye, students.